Hello everybody, I'm back again to talk more about entropy. We're in a note set called Entropy and Gibbs free energy. And so what I'm going to talk about today is, or in this video, is about entropy and state changes. If you're following me in the notes, I'm on page 6 of the unworked out note sets. So last semester we studied phases of matter, solids, liquids, and gases, came toward the end of the semester, and you recall that we can have phase transitions that occur. And so, for example, you at 0 degrees Celsius, for example, you're in equilibrium, it's an equilibrium condition under atmospheric conditions for the melting of ice. And so you're going back and forth from from ice to liquid water in equilibrium. So it's a reversible process. The forward direction rate, the rate of melting, is equivalent to the melt of freezing. So the melting point, just for goodness, so we get a few sig figs in my calculation, I'll define it as 0.0 degrees Celsius. It's known to a couple places behind the decimal. One of the relations we're going to use is for an equilibrium process like this. It's implied that it's reversible. Pretty much to have equilibrium, you have to have a reversible process. So one of the relationships that holds here, I will not prove it in this course, I'll just simply say it, is that delta S, and I'll still say delta S for the system. I'll use the term SYS for system so I don't have to write it all out. Eventually I'll drop that notation once we get to a certain form. Is equal to the heat, I'm using Q to be heat, over T. The temperature will have to be on a thermodynamic scale of Kelvin for this. So, remember, just in terms of units, this will have something like joules per Kelvin. This will be joules. So, a lot of times you have a process, they might talk about kilojoules converted to joules, and this will be Kelvin. This will be called the Clausius equality. Hopefully I can spell it right. Clausius equality, or Clausius relationship. So it's nothing to worry about. It's just the name of the relationship that comes out. So there's a problem. I'm going to work it out. It's a skill builder on page 6. It says under constant atmospheric pressure of 1 atm. So we have a constant pressure of 1 atmosphere. Calculate the change in entropy of the system when 1 mole of ice, so we're going to have 1 mole of ice, I'll put 1.00, 1 mole of ice melts at 0 degrees Celsius with delta H fusion. So that's the fusion associated with the forward process, is the melting, is 6.02 kilojoules per mole. The first thing you should see when you see that is the melting of ice is endothermic. And so it says report, we're going to calculate out delta S for the system. So we have this relationship, the delta S system, or sys, whatever I'm denoting it, is Q over T. The big thing to realize is that when you have constant pressure, remember this from last semester, when constant pressure, Q, the heat, is equal to the enthalpy. In this case, it will be the enthalpy of fusion because that's the enthalpy of interest for this process. So we have that over T. So that's the big, really for a lot of people, that will be the sticking point, is the relationship between the delta H associated with the fusion or melting of the ice and the heat. And so that's a link you have to know. And so now what we put in is, if it's, let's see here, we have 1 mole in the numerator, and because we're trying to get this ultimately in joules per Kelvin, 1 mole of ice, and then we have 6.02 kilojoules per mole. We have to get our units right. The moles will cancel, that's great. Let's convert it into joules, is what the problem asks for. So there's 1,000 joules per kilojoules. The skills you learn for dimensional analysis are big time important in this course. And then I also state here that this is at 0 degrees Celsius, so we're at 1 atmosphere. We'll have a reversible process here. This you add 273. If you want to do it more exactly, you can get a couple sig figs. You actually add 273.15 to it to get it in Kelvin. And that ends up, check my math, to be positive. And I'm going to put the positive here for emphasis, 22.1 joules per Kelvin. The kilojoules cancels here. You're just left with joules and Kelvin. So again, entropy has units of energy, joules preferentially, and then temperature in Kelvin. So underneath this, there's a conceptual skill builder. It says, since liquid, water, and ice are under equilibrium at 1 atmosphere and 0 degrees Celsius, it's equilibrium, it's on the phase boundary, what is the value of delta S universe? Well, in that case, for this process, when it's reversible or at equilibrium, delta S universe is 0, right? The second law is that for observed processes, delta S universe is greater than or less equal to 0. It's never decreasing. It's never decreasing. And in this case, when you're at equilibrium, or you have a reversible system, delta S universe is equal to 0, which means delta S universe is equal to delta S for the system plus delta S for the surroundings. So if this is 0, we have 22.1 kilojoules per mole here. That means that this has to be, delta S of surroundings has to be negative 22.1 kilojoules per mole. It's the negative of the other value. Excuse me, joules per mole. Joules per mole. But we calculate this in, I don't know why I said kilojoules. This is in joules per mole. So it's the same magnitude but opposite sign. So what's going on here physically is what? Think about it. You've got this ice and it's going to liquid water, right? So it's taking in heat. It's taking in heat. By taking in heat from the surroundings, you're actually lowering the entropy of the surroundings, which means we can write another set of rules for it. Since delta S of the surroundings is equal to negative delta S system in this reversible process, that means we can write it as equal to negative delta H over T, provided we have constant pressure for our reversible process or equilibrium process. So this is a very convenient relationship right here. Delta S surroundings is equal to negative delta H, which is a system variable, divided by T, provided there's constant pressure. So that's something to think about. So that's an important realization. An important relationship we're going to build up to, I'm going to derive it now. Drop my eraser, aka my napkin. So there's some more examples and problems you want to work through in the notes. and in the skill builder that deal with these type of calculations for other processes, but that's the gist of it. So we have a relationship now. One of the problems we have, so we got reactions going on. Let's just call it reaction A to B, some kind of reaction. We got a system, that's the system. And around it we got surroundings where we can clearly have heat transfer going on between it and the system, right? And so we have a big law. It's delta S universe equals delta S for the system plus delta S for the surroundings. That's great. One of the big problems you'll have is that when you do calculations to use this, we have an overall rule that delta S for the universe is greater than or equal to 0 for observed processes. That's really the second law. That's a mathematical way of writing it. We'll say it in different ways, but that's one way of saying it. That the spontaneous processes greater than 0, equilibrium reversible process equal to 0. And like I said earlier, if it's not observed, you can think of that as less than 0. But if you drive that not observed reaction to be observed, delta S universe is going to have to adhere to this law. So in a sense, for any process you see, driven or not, this law holds. The problem is closure on the surroundings. How to get numbers for that, because it's hard enough to measure things in the system, the chemical reaction. To measure the heat transfer to the surroundings is difficult. So we already have a relationship for a reversible process for this. We just said earlier that this was equal to negative delta H over T. That's a system variable. Let me make sure you can see that. So I'll say already we have delta S for surroundings equal to negative delta H over T for a reversible process. We can define a variable, a state function, we'll call it G, and talk about delta G. I'll write it as a definition. G denotes what's called the Gibbs free energy. Gibbs was a person, thermodynamicist. So it's one of the two main free energies. G is called the Gibbs, and there's another one called A, which is called the Helmholtz. We won't use it in this course. It's just, it's a little bit beyond the scope of what we're going to talk about. So this function works nicely. G is well behaved and works nicely under conditions of where you can, as a function of temperature and pressure, which is great because those are experimental variables that we can control in the lab. We can change the temperature of systems with a hot bath or an ice bath, and a pressure could be fixed by the atmosphere, but we certainly have ways of pressurizing the system. And just as a side note, the other free energy is the Helmholtz, and that's a function of T and V. That's pretty good too, but when you do solution phase chemistry that forms gases or consumes gases, the volume's hard to control. So we use this a lot in solid state physics and in condensed matter studies and so forth, theoretical physics. But for chemistry, this is usually the free energy choice, and that's what we're going to focus on. Definitely, if you go on to biochemistry, they'll focus more on the Gibbs free energy than the Helmholtz free energy. So we'll focus on the Gibbs free energy. So our goal is to get it such that we can measure just things in the system and predict spontaneity using that. So what we can do in that case is we could write delta S universe is equal to negative delta G over T. And let's just start plugging in here. So we'll plug that in for delta S universe here. I'm just at this point going to call delta S for the system just delta S, because that's what we're going to be using ultimately. And we have over here for the surroundings delta H over T. That looks good. Awful lot of negatives here, so I'm going to just multiply through by -1. Looks good. T's in the denominator. Let's just multiply by t. That's going to give us, let me just write it up here. So if I multiply through by t, I get delta G is equal to t minus t delta S plus delta H. Nothing wrong with that. The way it's usually written is delta G equals delta H minus t delta S. So this is more convenient to work with for real calculations than delta S universe is equal to delta S, I'll just keep it as that now for the system, plus delta S surroundings. We can measure heat transfer in and out of the system. That gives us delta H under select conditions. We can certainly make calculations better for delta S for chemical reaction in the system than heat transfer to the surroundings. And we certainly can measure temperature. So it ends up being just a much more pragmatic equation. Because of the fact that there's that negative relationship, delta G, we'll take it as a definition of T delta S universe, it flips the signs on the relationships. Delta G less than 0 is spontaneous. Delta G equals 0 is non-spontaneous, is equilibrium. It's equilibrium or a reversible system. And delta G greater than 0, just like before, is non-spontaneous. So the sign conventions are opposite, and this would be summarized on the bottom third of page 8. So that's actually a really powerful rule set. I don't like to say commit things to memory, certainly try to understand it. Go back to delta S universe, realize there's a sign difference in the convention of how we related delta G to T delta S. I try to write it over neat, I read it more sloppy. There's a sign difference here by definition, if you care to take it that way. We can go, there's more deeper math derivation, but we'll take it as a definition. So this defines spontaneity of processes. And I just want to make a side note, this is kind of FYI, it's a little, maybe a little hard to understand theoretically, but I derived this under reversible set of conditions because we end up with all state functions which are independent of path. I can use this type of relationship to describe reversible processes or irreversible process, so it has broad utility even though I derived it under constrained conditions because they're state functions are independent of path. One of the big things we try to do in thermo as much as possible is cast our main relationships not so much in terms of heat and work, but in terms of state functions because they do bear that property and allows us to derive equations that have broad utility. So that's a good rule set. Let's elaborate on it just a little bit more. So that's called Gibbs free energy, G, and delta G is just a change in Gibbs free energy. We usually work with the deltas more than the functions themselves because we look at differences. It is a misnomer when books say you can't calculate out U or H itself, you can only calculate the difference. That's not true, that's just saying it's hard to calculate it out absolutely. So there's a skill builder on the bottom of the page. Let's look at it. We'll use our relationship delta G is equal to delta H minus T delta S to fill it out. And I would definitely do this on my own. When you're sitting back, think about what we did just now and redo it on your own. There'll be conceptual questions on this on the test, no doubt. So let's take and we'll do a numeric problem in the next video because I'm running out of time. Let's take delta H and delta S and look at some conditions, and we'll say low temperature versus a high temperature. And what defines it as low and high is just either sides of some sort of a threshold. You know, we'll do a calculation. We calculate out what that exactly means in a little bit. But let's take some cases where we have a positive delta H, which would mean what? It means it's endothermic. Excuse me, I'll do it in the order I have it. Right? I have a negative first here. So we have a negative and we have a positive. We have entropy increasing and we're giving off heat. So when you look at this, doesn't that make it spontaneous under all conditions, right? So it's because this is negative. A positive here gives you, have a negative out here as a multiplier. Temperature is always going to be positive because it's on the Kelvin scale, which starts at 0 and goes up. So it's either going to be not existent or positive. It's never going to be a negative temperature here. You're not working in Celsius. So you're always getting a negative delta G here, meaning in both cases, I'll just write for spontaneous. It's spontaneous no matter what, as long as these functions don't change for this process, and we're just taking it as they have a certain sign. And so let's take the opposite case where this is positive, endothermic, and it's the delta S is going down. The system is going, like, let's say, from a gas to a liquid, something like that, where it's getting, in a sense, more organized. I don't really like to use that terminology too much, but the material has less degrees of freedom. In this case, it's always non-spontaneous. I'll just write non-spont for non-spontaneous. It's a big word. Because why? This is working against you being spontaneous, and now you have a negative times a negative giving you a positive, and a positive delta G is non-spontaneous. The cases where you have mixed relationships, we have a negative, and a positive, and a positive. So in this case, there will be a certain temperature below which you'll be spontaneous, and above a certain temperature, the same temperature above it, well, you'll be spontaneous. It will be non-spontaneous. So let's think about that. So the way I like to think of it, low temperature, let's just make this 0, because we can go to 0 Kelvin, so then delta G is equal to delta H in a low temperature limit, right? And so in that case, because you are exothermic, delta G is going to have a value equal to delta H, which is negative. That makes you spontaneous. Conversely, you can override at a certain temperature, and we'll figure out a problem numerically next time, your delta H with, when you have a negative entropy, you can override that spontaneity by a certain temperature comes over, and this T delta S term overrides it because you get a positive because of the negative multiplier. And it's the converse case in the one below it. I'll let you rationalize out the next case on your own, but that ends up being non-spontaneous and spontaneous for low T and high T regimes. So work through that, understand it in words and using the equation. Don't memorize it, because I'll have problems where it will show that you didn't memorize, you actually understand it. I'm running out of time on my clock here, but we'll work a numerical problem next time. Have a good day. Maybe I'll make another video.